Tutorial for today's GFG problem of the day, count set bit. So it's a pretty I would not say simple, but it's a good question. Like if you solve this one, you should be able to remember this pattern, and then this question becomes easy. So let's read through the question first. You are given a number n. Find the total count of set bits for all numbers from 1 to n, both included. Okay. Now the note here is that see n is around 10 is to the power 8. So what, like if you basically want, let's say n is 5. Okay, 1 second. And why is this happening? Let me use this. N is 5. So the numbers that we will have is 1, 2, 3, 4, 5. One would have one set bit. That is just one, right? One, what is two? Two is 1 0. So this also has one set bit. Three is 1 1. So this has two set bits. This has one set bit because it is just one. Four is 1 0 0. So this has one set bit. And five has two set bits, 1 0 1. So that is two. Now the final sum would be 1 plus 1 plus 2 plus 1 plus 2. And that is 2, 4, 6, 7, right? So this is the final sum or the final answer. Now what we need is this thing. But see, if we just go over all the values from 1 to n, 1 to n, this would take how much time? N. And for each number, we'll have to go over all the bits and see if it is checked or not. So that would be again 32 because see, it's an integer around 10 is to the power 8. So around 30 to 31 bits can be there. Right, so n into 32 or rather 10 is to the power 8 because can be as large as 10 is to the power 8. So the brute forcing the thing would take how much time? Around 3 into 3.2 into 10 is to the power 9, and this would obviously TL. Now, yes, you can argue that rather than go over all the 32 bits, we can go over all the set bits. But again, I think this would TL, and this is not the most optimal solution clearly. So, what is the most optimal solution if you ask me? The thing that you have to note here is that when we represent integers in binary, so let me write the first six, my first seven integers starting from 0. So see, this is 0 0 0, this is 0 0 1, this is 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and this is triple one. Now the thing that you have to notice that at the, let's say this is the first bit, this is the second bit, this is the third bit. So this first bit, or rather it's better, let's call them zeroth bit, first bit and second bit. So we are start from 0. So this 0 bit actually forms a group of size 2 raised to the power b plus 1. Every bit starting at will form a group of 2 raised to the power b plus 1, and this group would always get repeated. See, here it forms a group of size 2 and this gets repeated. That is 0 1 0 1 0 1 0 1. See, this happens. You can even go further in this, and you will see this pattern keep repeating. Again, for fun, it would form a group of size 2 raised to the power 1 plus 1, that is of 2 raised to the power 2, that is of size 4. And we can see this 0 0 1 1, this 0 0 1 1. Again, if we write down 8 here, this would be what? 1 triple 0, and see again this is same as this, and this would get repeated again. Then similarly here, this forms a group of size 8. That is 2 raised to the power 2 plus 1, 2 raised to the power 3, 8 of size 8. So this makes sense. Now, if we know that this group is of what size and also what's the group pattern, each group, if let's say it is of 2 raised to the power b plus 1 size, it would first have 2 raised to the power b zeros, then it would have 2 raised to the power b ones. See here, 2 raised to the power 1 zeros, that is 2 zeros, and 2 raised to the power 1 ones. If you do not know this result you should kind of remember, or you can even prove this because this is just modulos, right? Here, see, why is this same as this? Is under mod 4, these are same. Under mod 2p plus 1, the values that are same would get repeated. Here, this is same as this because see, here mod 1, here mod 4 is 1, here also mod 4 is 1, right? So you can even prove this. There's just another mod criteria, but here let's stick to the result that we saw. So if this is forming a group and we know what the group pattern is, can we know not go over, like if we know n directly, let's say n is something like 15. So 15 is what? 8, or rather let's use 30. 13. So this would be 1 what is, so 8 would be set, and then 4 would be set, then 2 won't be set, and 1 would be set. So this is 13, right? Now we know that, okay, for this bit, this is 0, 1, 2, 3, right? So for this bit, this has a group size of 2 raised to the power 3 plus 1, that is 2 raised to the power 4, 16. So what is the number of groups that this is in? This, that would be 13 by 16, right? This is in the zeroth group of this. Why a simple division works? Because see, if the number of groups, or okay, my bad. If yeah, so if there are some groups, this is group 0, this is group 1, this is group 2, right? If you are in group 2, if n is here, so n by group size should be equal to 2, right? Because all the groups are of equal size, right? So from here we can get the number of groups. Now in each group, how many, so here from this we get the group number. Now in each group, how many bits are there, or how many set bits are there? There's 2 raised to the power b set bits. So this is for each group, right? So here it is of, here the group would be 0. So 0 into, and the number of set bits is 2 raised to the power 3 in each group. So 0 into 8 plus, now see, here also it is set. Here also it can be set. So for the current group that it is in, we don't calculate the total bits, right? Because total bits are not in the 1 to n set. We only calculate how many of these groups, how many of these numbers are that have set bits in it. So how you can do this is, see here, what is the position of this in the in its group. So group is of size 16, so it is in 13 mod 16 position. As I said, this is just a modular position right here. See, the position of this is under 5, is 5 mod 4 equals to 1. This is 0th position, this is first position. In its group, this is second position. We can also say 6 mod 4. This makes sense, right? So this is at 13th position. Now for, we know that the first 2b minus 1 positions are all not set. Then rest 2b, or rather 0 to 2b minus 1 are not set, and from 2b to 2b, mm, from 2b it is set. So we just need to see how many of these n are, where does n lie in, does it lie in this set? If it lies, there are no set bit. If it lies in this part, 2b to n, then the number of set bits would be n minus, because see, n is also included and 2b is also included, so n minus 2b plus 1. Let me see, so show you the code. I think it would be a better explanation here. So yeah, I just go over all the bits, like all the bits position, and for each bits, I calculate the group size. As I said, it's b plus 1. You can change this to like b if it makes understanding easier. So p plus 1, and yeah, for each group would have how many count, and that is I'm storing it in count once. So that is 2 ratio or b. Now on the number of groups I calculate is basically n divided by group size. I add to my answer is, for each group I have this many ones, so the number of groups divided by count once. Then I calculate the n position. So in the current group that you are in, what is the position of n? That is n mod group size. Now if this position is greater than count once, because we saw that if it is greater than 2b, then only the this part has some one sets. Okay, my bad. Where is my this? Yeah. So if it is in this part, so 2b, 2, the group end, basically if it is in this part, then it has some ones. So here, like for 13, see, for 13, for the first bit, basically it is in 13, right? And the starting is like 8. So 8 to 13, all of them have these set bits, and we can even see from 0 to 8, this fourth bit is, rather the third bit is never set. It is something 0 0 0 0. Now at 8 this is set. At 8 it is set. It is 1 triple 0. At 9 it would also be set 1 double 0 1, because it is following the pattern that I showed you. 11 would be 1 0 1 1. 12 would be 1 1, and 13 is 1 1 0 1. So all of them have this set, bit set. So how many times this is? This is just 13 minus 8 plus 1, because both are included. 13 minus 8 plus 1, that is 14, that is 6. And we can even see 1, 2, 3, 4, 5, 6. Yeah, this makes sense. So if position n is greater than count ones, I just add this position n minus count ones because both of them are included plus 1, and I return my final answer. So yeah, this works. We submit it to prove it. Thanks for watching. I don't think this was my greatest explanation, but yeah, I'm a work in progress. Thank you. Bye bye.